Okay, this is going to be a video covering the first part of chapter 16 on acids and bases. So just to review some definitions, we talked about Arrhenius acid earlier. Arrhenius acids, when they are a substance that when they dissolve in water, they produce H plus or H3O plus called the hydronium ion. And a base is a substance that's when it's dissolved in water produces hydroxide ions or OH minus ions. We also talked before about Bronsted-Lowry acids and bases. And an acid is a proton donor and a base is a proton acceptor. And by a proton, we mean an H plus. A Lewis means that an acid is an electron pair acceptor and a base is an electron pair donor. Now, Bronsted-Lowry and Lewis are just opposites of each other. One is talking about being a proton donor. The other one says an acid is an electron pair acceptor. So it's looking at the same thing through the opposite way. All right, so for Bronsted-Lowry, in order to be an acid, you have to have at least one hydrogen that you can donate. So in the case of the reaction here, we have HCl reacting with water. We're producing Cl minus and H3O plus. So we can see that the HCl donated a proton to the water. So that H went over here and went to the water. That way, all that was left was the Cl minus, and then the water gained it, making H3O plus. Now, since we made H3O plus, this is the definition of an Arrhenius acid. So HCl is also acting as an Arrhenius acid, and it's acting as a Bronsted-Lowry acid. Now, in order to be a proton acceptor, it must have a pair, a lone pair of electrons that it can accept a proton. So in this case, you can see here's water and it's got two lone pairs, so it has the ability to accept a proton. Okay, there are some substances that can act as both acids and bases. So water is one of those substances. So here in the case of HCl, we saw that the H was donating the proton. So in this case, water was acting as the base because it accepted that proton. In the equation that's down below it, in this case, water is donating the H to the NH3 because on the other side of the reaction, it's NH4. So it accepted the proton. So in that case, water is acting as the proton donor, so it's being the acid. So water is one of those substances that can be an acid or a base, and we call those substances amphoteric. Now, all Bronsted-Lowry acids and bases are also Lewis acids and bases because we talked about those are the same kind of thing, but looking at it from the opposite way. Instead of being a proton donor, you're an electron pair acceptor. So if it's a Bronsted-Lowry acid, it would also be a Lewis acid. So for a substance to be a proton acceptor, we also mentioned in the slide before that it has to have an unshared pair of electrons in order to accept that proton. So in this case, we can see NH3 has this lone pair of electrons, and here it accepted the hydrogen, so now it's making NH4 plus. Now, whenever we have a reaction, an acid is going to produce a substance that's called the conjugate base. So the conjugate base is the substance that's formed when the acid donates that proton. And when a base accepts the proton, it produces the conjugate acid. All right, so the question says, what is the conjugate base of HCO3 minus? So the conjugate base of a substance is when that acid donates a proton, so we have to lose a proton. So if HCO3 loses a proton, it's going to be CO3 minus 2. And because it lost an H plus, not only did we lose the H, but we also lost a plus charge. That's why the charge changes to a minus 2. The next question is, what is the conjugate acid of HSO4? So the conjugate acid is formed from the base accepting a proton. So we're going to have to add an H onto the HSO4. So now it's H2SO4, and since we added H plus, it was a negative. When I added a positive, that then made it neutral. Now, some acids are better proton donors, some bases are better proton acceptors, and we can have a way that we can rank them according to their reactivity. And there's an inverse relationship, so the stronger the acid, the weaker its conjugate base. So if you have a weak acid, you would form a stronger conjugate base. And this chart shows that list of acids according to their reactivity. So we have the strong acids here on the top, and notice those are forming weak conjugate bases. And here, where you have things that aren't very acidic, they are forming strong bases or strong conjugate bases. Okay, so in every acid-base reaction, our equilibrium is going to favor going from a strong acid or base to a weaker acid or base. So in this first reaction, HCl is a very strong acid, so that means this reaction is going to want to proceed going forward, making K making K very, very large. Now, in the second reaction that we have, water is weaker than H3O plus. So in that case, the reaction is going to go to the left side, and K would be very small. All right, we already talked about water being amphoteric. So that means if water reacts with itself, it's going to, one of the molecules is going to donate a proton, the other one is going to accept the proton. So we're going to have it acting as both an acid and a base. Now, if we write that as an equilibrium expression, that means we would have H3O plus times OH minus over whatever the reactants are, in this case water. But since water is a pure liquid, it doesn't show up in my equilibrium expression. Now, this equilibrium constant for water is called Kw. Okay, and Kw at 25 degrees is 1 times 10 to the minus 14th. So that means this right here is 1 times 10 to the minus 14th. That means that we're going to be able to convert it between H3O plus and OH minus using this relationship. Now, if our H plus is greater than our OH minus, the H plus part is the acid part, the OH minus is the base part. So if those are equal, then the substance is neutral. If our H plus is more than our OH minus, meaning the acid part is greater than the base part, then we're going to be acidic. And if the acid part is less than the base part, then we're going to be basic. All right, so here they tell us that we have a solution in which the OH minus concentration is 0.01, and they want me to find the H plus. So here is that relationship that we're going to use. So I know the 1 times 10 to the minus 14th, if I divide by my OH minus, that's going to give me my H plus concentration. And then in part B, they give me a different OH minus, but again, the same process. 1 times 10 to the minus 14th divided by the OH is going to give me my H plus. Now this is also going to work if they gave you the H plus and they asked you to find the OH minus. You would take the 1 times 10 to the minus 14th divided by the H plus in order to get the OH minus. Now, pH scale is how we're going to be measuring the hydrogen ion concentration. And P means negative log. So if I do pH, I'm doing the negative log of my H plus concentration. And on our pH scale, a 7 is neutral, and our pH scale goes anywhere from 0 to 14. If we have numbers that are below 7, and those are going to be acids, strong acids are going to be clear on the end, like zeros and ones. Bases have a pH greater than 7, and strong bases are going to be clear at the opposite end, and those are going to be pHs of like 13 and 14. Now the sig fig rules for pHs are different than what we've had before. So if we look at the number of sig figs in our H plus concentration, that's going to tell us the number of decimal places that we have in our pH. And I told you earlier that P means negative log. So not only do we have pH, we have POH that we're going to be using in this chapter, and later we're going to be using pKa's and pKb's. So to find the pH, we said we do negative log of H plus. Well, if P means negative log, then the POH is negative log of the OH minus. And remember that the H plus times the OH minus is 1 times 10 to the minus 14th, but pH plus POH is equal to 14. So we have several relationships. So pH is negative log of H plus, POH negative log of OH, H plus times OH minus is 1 times 10 to the minus 14th, and pH plus POH is equal to 14. All right, in this case, we have freshly pressed apple juice, and it has a POH of 10.4, and they want me to calculate the H plus. So the first thing I did was I took the relationship of pH plus POH is equal to 14 in order to find my pH. Then I did the inverse of the log, which is 10 to the negative. So my H plus would be 10 to the negative pH to get my H plus of 1.7 times 10 to the negative fourth. Now, I could have done 10 to the negative 10.4 in order to find my OH minus, and then taken 1 times 10 to the negative 14th divided by that OH minus to get the H plus. So there's more than one method of doing this, or more than one way. All right, ways that we measure pH is we could use a pH meter. And so far in the lab, we have been using like pH paper. pH paper is not quite as accurate, but it's a lot quicker. In our acid-base titration labs that we're going to be doing later, we will be using a pH meter. Now, we can also use indicators to tell us if things are acids or bases, but they don't necessarily do a good job of giving us a numerical pH. And this chart over on the side shows me several different indicators and when they would change color. So if I were to look at methyl orange, it looks like methyl orange is red if you're acids, and it's yellow. And it looks like maybe about 3.8 or so is when that color change occurs. So if you have a pH of less than 3.8, it's going to be red. If it's greater than 3.8, it's going to be kind of yellow. If we look at something like phenolphthalein, it looks like that transition point is a little bit, maybe around 9. So it's colorless and an acid, and if it's greater than a pH of 9, it's going to be pink. Just to remind you, there are 7 strong acids, and those are the ones that are listed here. Strong acids, we also talked about electrolytes, and strong acids are strong electrolytes. And if we have a monoprotic, meaning only one proton, strong acid, the H3O plus or the H plus concentration is the same as the acid concentration. All right, so in this case, they've told me that I have the concentration of my acid is 0.040 molar. That means that the H plus concentration is 0.040 molar because it's a strong monoprotic acid. And to find my pH, I need to do the negative log of the H plus. And this has 2 sig figs, so my pH has 2 decimal places. Now, strong bases, on the other hand, those were column 1 and the bottom half of column 2 with OHs, as long as they are soluble. And we could write those. So for example, if this is an alkali metal, so like LiOH, it would split apart into Li and OH. If it's in column 2, like calcium hydroxide, then this would split apart into 1 calcium and 2 OHs. All right, so this one's wanting me to calculate the pH of a strong base. So it tells me that the pH of my solution is 0.028 molar. Now keep in mind there are 2 OHs. So the concentration of my OH minus is this times 2. So my OH minus is 0.056. My pOH then would be the negative log of my OH minus, which is 1.25, but they wanted me to find the pH. So pH plus pOH is 14, so I'd have to take 14 minus 1.25 and get 12.75. And my original number had 2 significant figures, so I have 2 decimal places in my pH. And that is the first part of chapter 16.